I'm going to talk about a tool for network debugging, SwitchPointer. This is a joint work with Rachit and Mingyan Lee from University of Edinburgh. Monitoring and debugging network problems is complex. There have been many recent works in the last few years, but it still remains a challenging problem. As the number of endpoints in the data center increases, higher speed and higher utilizations, debugging the network problems is still a challenging problem. So while this work tries to address the network problems, it is becoming increasingly harder. Why is that the case? Let's take an example. Consider that there is a low priority flow F1 and its throughput is close to 1 Gbps initially at both switches S1 and S2. When a high priority flow F2 came in, the packets got delayed and its throughput is dropped to 600 Mbps. And right after F2 finishes, another high priority flow F3 came in. Now the throughput of F1 is further dropped to 200 Mbps at S2. Now monitoring and debugging this problem require end host visibility to detect the problems. And we cannot do this from the switches because the telemetry data is distributed across multiple switches. We also need in-network visibility to debug this problem because we want to know what are the contending flows and also where the location is. To this end, there have been many recent works. I just want to categorize them into, on the one hand, we have in-network monitoring techniques that exploits the resources at the switches. Exploit the programmability feature at the switches, and then query this data using either new software or hardware interfaces, and then perform the diagnosis. Though these approaches provide high network visibility, they require a lot of resources. Limited by these resources, they have to rely on highly aggregated data or selectively sample network traffic or approximate counters, which sometimes may not sufficient enough to debug the network problems. On the other hand, we have end host based monitoring approaches that exploits the resources at the end host and also take the advantage of programmability to implement various monitoring and debugging functionalities. But the problem with this approach is they lose the visibility benefits offered by the in-network monitoring approaches. In this work, we present SwitchPointer that integrates the best of two worlds: network visibility of in-network approaches and resources and programmability of the end-host based monitoring approaches. SwitchPointer uses the end-host to collect and monitor the telemetry data. Rather than using the switch memory to store the telemetry data, SwitchPointer switches store pointers to the end host that has relevant telemetry data to debug the network problems. In specific, switch keeps track of the destinations to which it has processed the packets. When a spurious network event is triggered, the analyzer uses the pointer at the switches and identify the end host that has relevant telemetry data to debug the network problem. The key design choice of using switch memory to store the pointers to the end host rather than the actual telemetry data to debug the network problems allows SwitchPointer to solve many problems that are hard or infeasible for many existing system designs. In a nutshell, SwitchPointer switches divides time into epochs. In each epoch, it keeps track of it maintains pointers to the end host that it has seen in each epoch. In addition, switch also embed two pieces of information into the packet header: link ID and epoch ID. While link ID is used to trace the packet trajectory, that is the list of switches that the packet has taken, and the epoch ID can be used to efficiently track the contending flows and packets at individual ports. Second, end host, upon receiving the packet, collect and store the telemetry data that is carried in the packet header, and the end host also provide a query service that allows to filter the telemetry data stored locally. Finally, analyzer use the pointers when a spurious network event is triggered. Analyzer use the pointers at the switches and identify the end host that has relevant telemetry data to debug the network problems. Now let's revisit the too many red lights case and see how SwitchPointer debugs the this problem. When the destination of the red flow observed throughput drop, it raises an alert to the analyzer along with the switches in the path and also the corresponding switch epoch IDs. And then the analyzer retrieves the pointers to these end hosts. Next, it contacts the end hosts in these pointers, execute queries on the telemetry data stored at these places, and learn that F1 packets are delayed because of F2 at S1 and F3 at S2. Despite the simple design of SwitchPointer, it has mainly 4 technical challenges. First challenge is about finding the right epoch size and a data structure that provide a favorable trade-off between switch memory and bandwidth between data plane and control plane. In addition, it should also allows to efficiently retrieve the containing flows and packets at fine-grained timescales. Suppose if the epoch size is too small, then we need large memory to store a large number of pointers to the end host, or large bandwidth between data plane and control plane to persistently push the pointers, so to periodically push the pointers to the persistent storage. If the epoch size is too large, then the system might become inefficient because a switch might forward packets to a large number of end hosts in a large epoch. While analyzer try to debug the network problem, it might need to contact a large number of end hosts and filter the telemetry data, which may not be scalable. We resolve this problem using a hierarchical data structure where each subsequent level of hierarchy store pointers or epochs with exponentially larger timescales. Suppose if the epoch size is alpha, at level 1 there are alpha set of pointers and each pointer corresponds to the packets processed by the switch in alpha milliseconds. Second level also has alpha set of pointers, but now each pointer corresponds to the packet processed by the switch in alpha to the power 2 milliseconds, and so on. When alpha is 10 and k is 3, there are 10 set of points at the level 1 and each corresponds to 10 millisecond duration. Level 2 also has 10 set of pointers, but each corresponds to 100 millisecond duration. By design, switch pointers store redundant information. For example, the pointer at the level 2 is collectively similar to the set of pointers at the level 1. Precisely this redundancy allows SwitchPointer to have a trade-off between storage and bandwidth between data plane and control plane. When the number of endpoints are fixed, say n, as alpha and k increases, the memory requirements also increases. When alpha is 10 and k is 3, it requires 345 KB for 100 k end hosts. The agent running in the switch allows SwitchPointer to retrieve all the pointers at all levels. The pointers at the lowest level provides a fine-grained view of the containing flows and packets. This might be useful for the real-time diagnosis. And the pointers at the top level provides a coarse-grained view of the containing flows and packets, and this could be useful for the offline diagnosis. Moreover, SwitchPointer only pushes the top level pointers for every alpha to the power k milliseconds. So the bandwidth requirement depends on alpha and k values. When alpha is 10 and k is 3, it requires 100 kbps for 100 k end hosts. And the second challenge is how to efficiently maintain and update pointers in the data structure. One idea is to use hash table, but it requires either large memory to keep the collision probability low, or more number of operations per packet which may not keep up with the line rate. We resolve this problem using a minimal perfect hash function. The key observation is that the destination IPs in a network are known in advance and it changes at coarse timescales. So we exploit this fact to construct the minimal perfect hash function and completely avoid the hash collisions. And it requires 2.1 bits of storage for each end host. The trade-off is the construct time could be larger. So assuming that the number of end hosts in a data center changes at coarse timescales, we could keep the number of times to compute the perfect hash function less frequently. We represent a pointer using a bit array where one bit is assigned to each end host. When a packet arrives, the destination IP in the packet header is used to compute a it computes a hash operation, single operation, irrespective of the number of levels in the hierarchy. And The output of that single operation is used to set the bit in the bit array, and it is set across all levels in the hierarchy. Lookups are also easy. To check if a particular destination IP is processed by a switch, one just need to check the corresponding bit given by the minimal perfect hash function. And the third challenge is about how to efficiently embed link ID and epoch ID into the packet header. One idea is to use clean slate approaches like INT, but in this work we also present design that works for community switches in the current deployments. For this, we extend a link sampling technique called cherry pick, which is also our prior work, that actually allows to trace the packet trajectory. The key idea is to, instead of picking each and every link that the packet has traversed, you can selectively choose the set of links that represents the end-to-end path, and you just need to embed that link ID into the packet header. And the final challenge is about how to resolve, how to handle the fact that the network devices may not synchronize perfectly. We resolve this problem based on the observation that we can generally set bounds on the clock difference between any pair of devices. So we handle it by carefully designing the epoch boundaries in the switch data structure. You can find more details about them in our paper. To understand the switch pointer coverage, we studied the problems that are addressed in the recent works, both in network monitoring approaches and end-host based approaches. And since the main idea is to add network visibility to the end-host based monitoring approaches, we almost support the end-host based problems that are supported by the end-host based approaches. In addition, we also support a large class of network monitoring problems that are supported by the in-network monitoring approaches. In addition to these, SwitchPointer can debug problems that are temporally and spatially correlated, that are hard to debug these problems with the current existing designs. And temporally correlated problems are those that occur because of switch events at a specific switch, whereas spatially correlated problems are those that occur because of events that are distributed across multiple switches. You can find more details about the supported applications in the GitHub repository. And some of the applications that SwitchPointer cannot debug are those that requires instantaneous queue sizes and overlap loop detection and properties of a packet at a particular switch. You can find details in the GitHub repository about them too. Now let me explain a bit more complex example that shows the capability of the switch pointer. Let's consider there are three flows, F1, F2, and F3. F1 is the highest priority, and F2 has middle priority, and F3 has lower priority. Initially, F1 starts at 0 and ends at 10, and F2 starts at 10 and ends at 20. Right after F2 finishes, F3 starts at 20 and F3 ends at 40. You can see that there are no overlaps between start and end time, so there is no collision. Now let's see the cascading problem. As usual, F2 starts at 10, but F1 is delayed to 15. By then, since F2 is already started, the packets, F2 packets are delayed, and right after F1 finishes, F2 resumes back to the normal state. But the problem is, by then F3 is already started at 20. So the F3 packets are delayed, and right after F2 finishes, F2 resumes back to the normal state. So if you notice, the flow completion times of F2 and F3 are greater than what we observed in the previous case. And to summarize this, the F1's impact on F2 is cascaded to F3. Now let's see how SwitchPointer debugs this problem. When the destination of the F3 raises an alert to the analyzer, it retrieves the pointers to the end host, and then contact these individual hosts, filter the telemetry data, and learns that F3 packets are delayed because of F2. And analyzer repeats the same steps for the switches in the F2 path, and learns that F2 packets are delayed because of F1. Of course, debugging this problem could be more complex than the example shown here, but we use this example to demonstrate that it can debug temporally and spatially correlated problems. To understand the packet processing overhead at a switch, we compare the throughput of SwitchPointer with the OVS DPDK version, and On the x-axis, you can see the packet size varying from 64 to 1500 bytes, and we observe that the SwitchPointer throughput, SwitchPointer doesn't observe any throughput drop when the packet size is greater than or equal to 256 bytes. And in specific, we observe that when the packet size is 128 bytes, that the SwitchPointer has 22% throughput less than the OVS. We envision that this limitation can be overcome with hardware implementation on top of the programmable switches. To conclude, SwitchPointer is a system that monitors is a monitoring system that integrates the best of both in-network monitoring approaches and end-host-based monitoring approaches. SwitchPointer switches operate switch memory as a directory service and use this directory service to add network visibility to the end-host-based monitoring approaches. And the evaluation of SwitchPointer demonstrators can debug a large class of network problems that includes both temporally and spatially correlated problems. As part of the ongoing work, we're currently working on hardware implementation on top of P4 and network PGA. I hope you enjoyed the talk. I'm happy to take any questions. Thank you.
Questions? You can ask questions, I won't mind. Okay, I will not offer chocolates, but you should ask tough questions. So Praveen, okay, I know everything about this work, so I'm going to ask him an easy question. So how do you envision, so I think the broader thing that we talked about in this paper is whether you should partition the functionality at the end host or at the in-network switches. Where do you see this? Do you think that SwitchPointer settles that problem, or is that question worth exploring even more? That what functionality should be implemented at the end host and what functionality should go in the network?
Yes, there's still a bunch of problems that we still need to look into. Say, for example, performance-related problems that requires more fine-grained view of what is going on in the queues, for instance. So how to enable these features from the end-host-based monitoring is something that we are currently looking at.
Sanjay?
Yeah, so one question I had was, you're sending these messages to the directory server or whatever, but right at the time of the performance problem. So you're reporting telemetry data across the network.
Mm-hmm.
But if you have a performance problem, can the reporting the telemetry data itself be impacted?
So,
or I might be
in this
misunderstanding.
work, we are not sending any probes. We are actually embedding the pack information, telemetry data into the actual network traffic. So that way you can detect the problem as and when it happens at the destination end host.
Okay. And one other question is, can you see this being used? Is this primarily done in a data center context, or could you imagine this being used, say, in an internet?
We haven't done any work in that direction. Probably in the future we'll look into that.
Okay, thanks.
Hello, I'm Dot from Brown. I have a question. So in this work, you mentioned that the pointer is largely stored in a hash map that is based on destination. Have you ever considered any encapsulation problems? Because in a data center, encapsulation always happens like SLB, something that. Can you detect some question like overlay loop, something like that?
Yeah, there is a limitation with overlay finding out the overlay loops case from the end host. Yeah, that is one of the, I mean
the encapsulations.
Encapsulation actually hides the information, yes.
Yeah, because of based on destinations if that changes.
That requires some additional functionality to be implemented at the end host, and also additional parameters to be added to the system.
Okay, thanks.
This is a clarification question. So you are storing some data structure at the individual switches, right? And typically for the switches, you would have, if not hundreds of thousands of flows or millions of flows, maybe thousands of flows, right? So have you looked at any algorithms where when you get this information from the switches and information from the end hosts, how can you pinpoint or identify a smaller set of nodes that are problematic. So have you run into issues with respect to, for good flows versus bad flows, you have lots of them. There might be some non-deterministic, maybe some flows are having issues in the first 5 seconds, may not be in the next 5 seconds. What sort of techniques or algorithms do you have? Maybe I missed that in the paper, but do you have some things about how to detect problematic flows?
So from the switch perspective, I think one doing it at the switch requires some additional per packet operations to do that, if I understand correctly, to make sure, to see how the flow is performing, right? So we haven't done in that direction actually how to make sure how you can compute some kind of how the flow is doing from the switch. No, we haven't done that in that direction, but we did it from the end host direction. How to compute how the flow is performing. Are there any delays are going on at the end host, but not at the switch side.
Okay, thank you.
Thank you.